Hey everyone, two things. One, the camera's off because I have bedhead and I'm just not in the mood. Two, I'm trying my other mic. I don't expect it to be better, but whatever, we'll just see what's going on. So what we're doing is a quick walkthrough of the first evidence assignment from Target 7.2. I don't plan on making a ton of these videos for 7.2, but I'll at least give, I think we've done one so far. This will be the second. I think I'll probably give you a third. But at any time, if you want, I will gladly go through and do more for you, okay? Just come and talk to me, email me, ask me questions, and we can make this work. So we have a car. That's driving through a valley, and the valley is roughly circular in shape. Here, let's show that right here. So valleys, yeah, roughly circular. Hey, can it not happen while I'm doing a video? Sorry, kids are, there you go. The valley is roughly circular in shape. And we have a car traveling through it. So let's just walk through our questions right here. Car drives through a circular valley as shown below. It has a mass of 1,500 kilograms and a speed of 12 meters per second. The radius of the valley is 35 meters. And when I say the radius of the valley, I literally mean this sort of circular shape that matches the valley is a 35-meter radius circle. Is the car accelerating? Explain. All right, so first things first. The number one thing you have to be able to do is to recognize the circular motion. Can you tell that there is a circular motion going on? Because before I drew that circle, it's not super obvious. Like, you don't see a circle in here. In fact, had I not drawn that radius thing, it might be really tricky to see that circle. But there's definitely a circular motion here. Our car is moving. So I'm going to draw like a little motion map for this to help us think about the next question. So we have the car and it's traveling on this circular path. So I'm just drawing little dots on it, right? So it's not always circular. So like in this area, it's not a circular path. In this area, it's not a circular path, but all along here, it's a circular path. And so we would expect this model to work. Now, as far as the velocities go, let's think about it. It's traveling this direction here, and this direction here, a little smaller, and this direction here, and this direction here. Do you see how the velocity is changing? Look at this velocity compared to this velocity. It's a very different velocity. Now, it's the same size. They're both 12 meters per second, but they're 12 meters per second in different directions. Just because something isn't changing speed doesn't mean it isn't changing velocity, because velocity is both speed and direction. So our velocity is changing the entire time. So is the car accelerating? Yes. It is, let's zoom in a little bit. It is not changing speed, but it is changing direction. All right. Good. So we have an object that's moving in a circular path. If you have something moving in a circular path, it means that the net force on the object must be central to that path. All right, that's probably the biggest takeaway that you need to have. If you ever see something moving in a circle, in a circular shape, that means the net force is always pointing towards the center of that circle. You need to be able to recognize that. That's something I expect you to be able to do. All right, so we're going to go ahead and draw a free body diagram for the car. just to start thinking about what's going on here with the force. So we'll say here's my car, and we're doing at the very bottom down here, right? So what are the only forces acting on the car? Well, there's gravitational force. So I'll do the whole on by right now. And then there's normal force, and that's it. Well, are these balanced? I mean, that's a good question, right? Like, are these going to be balanced? Well, go back and look at your answer to question 1. If they're balanced, there will not be accelerating. Acceleration only happens when you have unbalanced forces. We are definitely accelerating here. Our car is moving along a circular path. So because we have movement along a circular path, it means that we need a net force pointed towards the center of that path. So the net force on this car must be pointing towards the center of this circle. So I need an upwards force here. Now, over here, I'm going to need a kind of a up and right. Over here, I'm going to need up and left. But we're specifically asked about down here at the bottom. How much of an upward force? We need an upwards net force. So let's go look here. If I need an upwards net force, it means that this cannot be balanced. In fact, it means that our normal force must be bigger than our gravitational force. This is the only way we're going to get that centripetal upwards net force. All right. So let's think about the actual values on these. So the centripetal force, the force pointing towards the center of that circle, is the normal force. So we got to make this work. We need the normal force big enough to overcome that gravitational force. So let's work this out. We have a car. We know the car is 1,500 kilograms. So we know that the size of this force of gravity will be equal to 1,500 kilograms times 10 newtons for every kilogram, which ends up getting us 15,000 newtons. Well, this normal force has to be bigger than that. I don't know exactly how much bigger. We're going to have to figure that out in a second, but it has to be bigger than 15,000 newtons. So let's work out how big it has to be. Well, we know that the amount of force it takes for something to move in a circular path is equal to the mass times the velocity squared divided by the radius. So let's look at this. So the mass is 1,500 kilograms. The velocity is 12 meters per second. But we got to square it. Divided by the radius. Radius was 35 meters. This is a 35-meter radius circle. All right, so I'm going to go ahead, start with the calculator that you guys can't see, and run through this real fast. So 1,500 times 12 divided by 35 is 6,171 newtons. That means that my net force must be upwards at 6,171 newtons. But that's the net force. That's the amount that needs to be unbalanced. So this force needs to be bigger than this 15,000 newtons. I know that when I put together my normal force and my gravitational force, they have to add together to this 6,171 newtons. This is upward, so I'm going to make this one positive. So if the force of gravity we know is 15,000 newtons. What does the normal force have to be to make that add up? Well, it's going to have to be 2171. Wait, if I can do my math here. 171. So, with sig figs, 21,000 newtons. So this must be a 21,000 newton net force. Or sorry, normal force. So looking back on our car, we do have an upwards force and a downwards force. The upwards force is bigger than the downwards force, which lets it go in this circular path. Yeah. All right, so this is the first overview of one of these targets. I hope you see that mathematically this is a little bit simpler than the last stuff we were doing. There's only really one equation. We don't have to break everything to horizontal and vertical. But I do think conceptually this is more difficult. You have to be able to recognize what circle it's moving in. You have to be able to recognize how multiple forces can add up to be some sort of centripetal force. So go ahead, try this out. Let me know if you have any questions, and I'll keep posting evidence problems as we go along. All right, everyone. Let me know if you need anything. Have a nice day.